Okay. So we have a potential difference. We have a positive and a negative. And we have current flowing. The current is due to the difference in potential and the available free electrons. So once we have a potential difference, free electrons start moving. Now, it is not like a sprint, right? It's like we have a number of electrons in the conductor, right? That's for argument's sake. So it's not like this electron gonna run from here over to here. What happened is that once you energize, these start moving around. So this electron hit that one, transferring energy from this one to that one, and it continues along. So it's a continuous transfer of energy. So this is called drift. So here we say the moving electron strike the adjacent atom and rebound in a random direction. So it's going all over the place. So the energy or the electron drift. After some time, the electrons attain a constant average velocity called drift. Drift velocity. The current constituted due to the drift of such electron in metallic conductors is called drift current. So the drift current, the drift velocity is related to the electric field. In other words, if you have a 10-volt battery and you have a 20-volt battery, the electric field due to the 10-volt is going to be less than due to the 12-volt. So your electric field will be greater, but it's directly proportional to the velocity at which the electron move. This constant of proportionality, so VD, the drift velocity, is directly proportional to the electric field. So you know, if you have a direct relationship, which this signifies you replace this with an equal sign and a constant. The constant here is called the mobility of the material. So the unit for this constant known as the mobility is velocity over the field. Velocity is meters per second. Field is voltage per meter. So mobility is in meter square. Bring this up. Volt second. So these are some typical values for mobility. Aluminum, 0.012, 0.0012. For copper, it's about 3 times, right? So it's no surprise then that we prefer to use copper for conductors. Right?
Sir, higher the mobility, better it is.
Yeah, man, the more conductive is the material. So the ideal material now to use for your conductor would be what? Gold. But you can't imagine.
Expensive, sir. Better than
You can imagine if it was gold for your
Sir,
JPS.
so gold would have a mobility of like 0.0005 or so, a high number like that.
Yeah, man, I don't remember. You can check it out.
All right.
But it would be very high. But you can imagine if you use gold for running JPS, well, we wouldn't get any current. And man would eat the food.
unless it's in abundance.
Which now go happen again. Because the man them who have a little gold them just keep it to themselves. Anyway, what's
So,
J again? Eh?
so you would have better to use gold and platinum, or gold is cheaper. So,
Platinum. Which one have a higher conductivity? Google it now while we are talking. Google it. Google the conductivity of gold and the conductivity of platinum. And see which one. Or the mobility. Mobility of gold, the mobility of platinum. I think gold is have a higher mobility still. But you can check it out. All right. According to the relationship J and the velocity, we can write J equal rho v times the velocity. Because if you look at it now, what's J again?
current density.
J J is the current density, right?
Yes, sir.
So J then would be the electrons, the rate at which an electron across a surface. And so it would be the electron, which is the charge density times the velocity. The charge density can be obtained as a product of the number of free electrons per meter cube and the charge E of one electron. Thus, charge density equal M times E. Right? So if you do that little maths, J equal charge density times the mobility times the electric field. No.
Sir, is that a negative, sir?
Yeah, because because of the electron charge. The electron is going against the electric field. That's why it's negative. No. Remind me, what is Ohm's law?
So what you want? Equation?
Yeah, man. Anyhow, you can chop it up, give me.
Voltage equal current times resistance, sir.
How we come by that? Then just tell you that, eh?
Yes,
So
sir.
let us, eh?
I mean, how we come to the equation, sir?
Mhm.
Sir, I think our voltage is directly proportional to current
Mhm.
with the resistor being a constant.
Okay.
Oh, you mean like how we derive it from like first principle, sir?
Mhm.
And that you thought, oh.
Right.
I know that it has something to do with measuring the drift velocity, the drift velocity of the electrons, and that's how we get the current based on that. And but I don't remember how the voltage is calculated.
All right. Let us look at it in detail now. J is the current density equal the conductivity of the material times the electric field. Right? The conductivity is measured in moles, which is 1/ohms. This is what is known as Point law, Ohm's law. The V equal IR comes from this. Let me show you. Here we give you some typical value of conductivity. Here again, that's for aluminum, that's for copper. Conductivity equal rho E times mu. So let's go to relate that to what you knew all along. So we're gonna have a conductor of length L. Right? We apply a voltage across it. Right? Uniform cross section S as shown in here. The direction of E is same as the direction of conventional current, which is opposite to the flow of electron. So electric field, look at it. Is V over L. We agree? Electric field is the potential difference over the length of the conductor.
Yes, sir, agree.
Sir, the length I have in the diagram, sir, which length is that, sir? That I'm not sure how far the length was, sir.
Call it this.
All right, sir.
Now, the conductor of cross section S. So the current, because you have a cross section, and the current now would be equal to J dot ds, which is the cross section, the area times the current density. I agree with that.
Repeat that, sir.
You have a you have a cross-sectional area. Your current density J is your current per unit area, right?
Yes, sir.
So your current would be your current density multiplied by the area.
Yes, sir.
So look at this now. Look at this equation. So we say I equal the integral over the surface of J dot ds. The thing is that only the normal component, if you do J dot ds, only the normal component remains in your equation. So you can just drop the J dot ds and write Js.
Say that bit again, sir. Only the normal component going to be calculated, going to result.
This
And
is
it's
your
because of the dot.
electron. Your electrons going across your ear, right?
Yes, sir.
So it's your current density, which is the number of electrons per unit area times your area. So J dot ds will just give you the normal component because,
Oh, because of the dot product we're using, sir.
right. So it just amount to J times S. So we divide by S, J equal I over S, which is sigma E from above. So J equals sigma B over L. Using this and this. And solve for J. So J B equal JL over sigma, which is IL over sigma S, which is equal to L, the length over sigma times S times I. So this L over sigma S is your resistance. If you do this, V over I equal this, so this L over sigma S is your resistance.
So what that said, the S is the cross-sectional area?
Yes.
Okay, okay. Oh,
Sir, what is the unit of conductivity again? I can
Is
do it. I know it.
1 over the unit of resistance, which is moles per unit length. This turn upside down.
Sir,
1
what was
over,
it again? The symbol is X S, sir. Is that sigma? No.
which one? Hold on, let me answer the conductivity question first. See there. So you just flip the Ohm sign upside down.
Oh, and that. Okay. Can you answer my question same time? Thanks, sir.
Yours get answer too?
Yeah.
Come on, when I want it. So.
Hey, so. It's fine. Never mind. Thank you.
So the ratio a potential difference between two ends of the conductor. So the current flowing through it is the resistance of the conductor.
And this is how we get V equals I R.
Exactamundo. Equation 12 is nothing but the Ohm's law in the normal form given by V equal IR. So, let me show Ohm's law and you answer, hold that, it come from somewhere, yeah? So, let us look at it a little bit more. For non-uniform fields, the resistance R is defined as the ratio of V to I, where V is the potential difference between these two specified equipotential surface in the material, and I is the current crossing the more positive surface of the two into the material. Mathematically, resistance for a non-uniform field is given by V over I. And we know that V is the integral E to A E dot dl, and I is the integral over the surface of J dot ds. So this is Ohm's law. I'm getting ready to restart this thing, okay? So here we go. All right, so properties of the conductor. Read through that and tell me if you have a question.
So when you say static condition, sir, you mean like neutral condition, right?
It means like steady state.
All right.
You say, yeah, that's interesting. That's an excellent question. Because what we have been doing so far in everything is that we are looking at like the behavior of electric field as it is just there. We're just there. But you know, the reality is that it's not like that. So what we are really doing is that we have an electric field and we take a snapshot. We take a picture of that and study that. in electromagnetics too, where we start look at microwave and transmission lines and stuff. What we add now the time varying component to all of these things that we have been looking at. Right? So electromagnetic one, we call it, we are looking at static fields. Right? But really and truly, that not really exists. We just take a snapshot of electric field and study that as a beginner. You with me? Not to diminish the importance of it, you know, because if you don't understand this, you can't understand the dynamic field. But the point is that there's no such thing as static field. Hope you understand that.
Kind of, yeah.
It's like you can't study the static flow of water through the pipe, right? But you can take a picture in time and study that behavior.
Oh, that was what I mean. Oh wait, sir, I have one more question, sir. Go back up. Go back up, sir. I have one more question. When it's within a conductor, the charge density is always 0. It mean when it is static or like just always.
All right. The fact of the matter, right, is that if you have a conductor, right, I don't know if you probably hear it like the current flow on the surface of the conductor, right? And how far deep into the conductor the current flow is called the skin depth, right? That's something that we will study in microwave and all of that. But that's the skin depth. But the fact of the matter is that the field is on the surface or close enough to the surface. Within the center of the conductor, you wouldn't have any any charge. It would be on the skin.
So you
So
don't always think the other way around.
Eh?
You want to flow in the middle and not on the surface.
No one on the surface is that thing.
Oh,
So, sir, just to clarify one more thing, it's possible to have voltage or like current flow while the charge density is 0.
Voltage what?
Like current flow, sir, like a flow, the electrons flowing.
No, you remember one of the examples that we did last week. I think that was for a cable where they said how did that go again?
the coaxial cable.
Yeah, but we wanted to calculate the charge in certain region. Was it that or the electric field? Where we have one cable and we want to find, we want to have one cable and then we have the other one outside. And we want to find the electric field in different region. Oh shit. I remember we did the problem where we found the electric field from 0 to the inner surface of the first conductor and the outer surface of the first conductor and the inner surface. But outside now, but we said that the solution to that, if I remember correctly, the solution to that particular example was that from the center of the inner conductor to the inner surface of the radius of that conductor, there was no electric field because we use Gauss law, right? So when we did the Gaussian surface, there was no charge enclosed. You remember? You can hardly remember. Much less. Let me see if we can do this.
Yes, sir. It did.
We had
But
this,
we kind of get what you said about the surface.
and we had this, right? But when we did the example, and we used the Gauss law from here to here, right? What's Gauss law again? But there was no charge enclosed here, right? But then when we go out here, the charge, we found that the charge was here. And then we go up to here, right? Because this is the conductor carrying the current one way and this coming the other way. So we say the charge enclosed in here. The way the problem worked out was that we get no charge enclosed here. But that's the reality of conductor. But we didn't say it there. We were just studying Gauss law. Right? So we didn't mention that. But this this says it all. Charge is really just on the surface.
Oh, understand.
The more you know, sir.
Okay.
Hmm?
Sir, it makes sense, man. Well, to me.
Okay. This I want to just record, and it's just reading. Dipole and Let's see. The boundary condition. Okay. At 2 o'clock, we're gonna pick up from boundary condition for half an hour. Half an hour, we're gonna do boundary conditions. And then, let's see how long that is. Yeah. We're gonna do boundary condition for half an hour. And then we're gonna do some examples.
All right, sir.
Okay.
Okay, sir.
So see you at 2.
All right, sir.
So, sir,
Yeah.
I just wondering, like, how much of this is like applicable to real world conditions and in terms of
Well, I don't know. You think I'm gonna answer your question by asking you one. You think Ohm's law is applicable to real world condition?
yes, sir.
You use it every day.
Sir.
So this is just showing you where them things come from.
Oh, so when we start considering like drift velocity, it kind of brings the time conditions into perspective, you know, in a sense.
Right. Like for example, I'm bear this in mind when we come back at 2. We're gonna look at boundary condition, right? But if you remember from CXC physics, them tell you that when light travels from one medium to the next, you experience refraction and reflection, right? And we then call that again Snell's law.
Yes, sir.
So but light is an electromagnetic wave. So what we're gonna do now, we're gonna show you how that come about in a general sense for any form of electromagnetic wave, right? So that will help you in your design of shielding and all of those things. It's all relevant, man. Yeah. But most of us are, you know, even when we leave school, we just end up with a technician job. We don't really go into the thing and start designing like magnetic shielding and, for example, you have great engineers, famous engineers who make their entire 50-year career is just to design packaging for like computer chips and all of that, or even the insulation on cables. So it's all relative. It's just where you end up. With me?
Yes, sir. Put everything kind of get clear now. So.
Glad I'm happy with that. All right, so see you at 2.